Welcome to this Junior Cycle Higher Level Maths revision video, and today we're revising quadratic sequences. We're going to look at how to identify a quadratic sequence, finding the general term of a quadratic sequence, and also creating a quadratic sequence from a given pattern.
So let's first look at how to identify a quadratic sequence. So let's consider this sequence here, 1, 4, 9, 16, 25. So as we would have learned in the previous video, we will always look at the differences. So when we create our first differences, it will look like this. We add 3, we add 5, we add 7, we add 9. So these are our first differences, but they are definitely not common. So we move into creating or to calculating our second differences, which are the differences of the differences. And we get this here. So we see that we don't have a common first difference, but we do have a common second difference. And that common second difference is how we know that that sequence is a quadratic sequence. So the general term of a quadratic sequence contains a squared term, so it looks something like an n squared, an n, and a constant. So an n squared plus 2n plus 1 is an example. So there could be a coefficient in the n squared, there could be a coefficient of the n, and then there is a constant. So let's take a quick look at an example. Only one linear pattern begins with 1 and 7. Fill in the 3 boxes so that this number forms a linear pattern. Okay, so based on what they've told us and what we know from our previous video, a linear or arithmetic pattern has a common first difference. So I know I've added 6, so that means to get to each next term, this is the term to term rule, I add 6. So I add 7 and 6 and get 13, 13 and 6, I get 19, 19 and 6, and we get 25. And that is the only linear pattern that exists, because having that 6 that we're adding that first time, if it's a linear pattern, we have to keep adding that same 6. So then it says many different quadratics begin with 1 and 7. Fill in the 3 boxes below so that the numbers form a quadratic pattern. So remember what we know about quadratic. Here, yes, I'm adding 6, but the next time I add a number, it's not going to be a 6. But what I do know is common is the differences of the difference. So let's do this as my second difference is add 2. So if I was adding 2 each time. So in the first one I add 6, so the next one I will be adding 8. In the next one I would add 10. The next one I would add 12. And the next one, if there was one, I would add 14. Okay, so what does that look like? Well, we get 7 plus 8 is 15. 15 plus 10 is 25. 25 plus 12 is 37. Now that's only one possible one. You could do this so that the common second difference, the one that's in red, that was a plus 1. You could do that so it was a plus 3, a plus 4, whatever you want. As long as that's the piece that's common and the green piece is the first difference there is changing. So example 2. Orla is asked to write down a quadratic sequence, and she writes down the following. Exactly one of the terms in Orla's sequence is incorrect. Write down the correct quadratic sequence in the space below, and you may only change one of the terms in her sequence. Okay, so the first thing we're going to do is we're going to look at the first differences here. So we add 1, then we add 3, then we add 5, then we add 8. Okay, so straight away that looks a bit strange. Plus 11. Okay, so you notice that there was kind of a pattern in those first differences, 1, 3, 5. So really the two that we're kind of worried about straight away are these two here. And what we could say about these is, well, actually, based on what I know about my sequence, I feel like that should be plus 7 and that should be plus 9. The reason we know that is because the second difference is plus 2. So we're adding 2 each time. This one, to go from here to here, we actually added 3. Then we added nothing. And then we added 3. So here, we want that actually be plus 2, and plus 2. So you might see it without doing the second differences. You might have to get to the second differences to do it. But basically then, the one that's causing all my problems is my 22. So 14 plus 7, that should get me 21. 21 to 30 does give me the plus 9, which is correct. And then plus 9 to plus 11 gives me plus 2. So by simply changing that one term to 21, it creates the correct quadratic sequence. So you might be able to see that straight off. You might have to do a bit of work with that. That is absolutely fine, whichever way you work. And this is the one which we have changed. So now let's talk about the general term of a quadratic sequence. So all quadratic sequences have a general term, Tn, in the form Tn is equal to an squared plus bn plus c, where 2a is equal to the second difference. That's a really important piece of information. Without remembering this, you're going to really struggle to work out your Tn, your general term. This question is actually quite a difficult one because of everything which is involved in it. We do see it appear on the paper, so it's important that you remember this formula here and also this key piece here, that 2a is equal to the second difference. So now let's look at an example to find the general term of a quadratic sequence. So find the general term of the following sequence: 2, 8, 18, 32 and 15. So always check if the sequence is linear or quadratic. So we're always going to check, because in this case, although I said it in the heading, the question itself did not tell us it was quadratic. So let's double check. So we'll check our differences. So we add 6, add 10, add 14, add 18. Okay, so we definitely don't have a common first difference. This is definitely not a linear or an arithmetic sequence. Let's check our second differences. Add 4, add 4, add 4, and yes, we do have a common second difference. Therefore, it is quadratic. This is not a waste to do, because you look at it and say, oh, well, it's definitely not linear, because we need to have that common second difference anyway. So we're going to use this formula, which is Tn is equal to an squared plus bn plus c, where 2a is the second difference. So I know that 2a in this case is equal to the second difference, which is 4. So dividing both sides by 2 gives me a equals 2. So I can actually update this to say that Tn is actually 2n squared plus bn plus c. So I'm just going to move to a blank page to give a bit more space. And just to bear in mind, we're going to need to remember that our first term is 2 and our second term is 8. So I said first term is equal to 2, second term is equal to 8. So far we have 2n squared, sorry, now let me correct this, 2n squared plus bn plus c. So what we're going to do is we're going to use the fact that we know that T1, which is given as 2 times 1 squared, subbing in for n, plus b times 1 plus c, should equal 2. So we get 2 plus b plus c equals 2. So working and taking a 2 from both sides, you get b plus c equals 0. So what we've done is we've created an equation in terms of b and c, which we're going to be able to use to figure out what those variables, or well, in this case, those constants are. So now let's look at the second term. 2 times 2 squared plus b times 2 plus c, and the second term is 8. So 2 times 2 is 4, times 2 is 8, plus 2 times b is 2b, plus c is equal to 8. So in this case, taking an 8 from both sides, you get 2b plus c is equal to 0, and that is our second term. So now we can use simultaneous equations to solve for b and c. So we get b plus c equals 0, 2b plus c equals 0. So what I'm going to do is I'm going to multiply the top line by minus 1 so that we can eliminate the c. So minus b minus c equals 0, 2b plus c equals 0. Our c's eliminate and I'm left with b equals 0. I go back to equation 1 and I say b plus c equals 0. So if b is 0, then c must also be 0, which gives us our final answer of Tn is simply 2n squared plus 0 plus 0, which we don't need to put in, but it just gives us Tn is equal to 2n squared. So now let's look at getting a quadratic sequence from a given pattern. So the first 3 stages of a pattern are shown below. Each stage of the pattern is made up of small squares, and each small square has an area of 1 square unit. Now that's very important. We're going to be using that as the question progresses. It then asks, draw the next 2 stages of the pattern. So this is what they look like. Often students struggle with this. And one suggestion I would make is, let's take stage 3 here. So if you first of all show your previous stage in one color, so I'll show stage 2 in red, and then you can see what you've added on. So for stage 4, let's do the same. Let's highlight then, or what you would do if you were drawing it. Let me just rub, I've gone too far. So if you were drawing that, you would draw stage 3 first and then build on it. So let's highlight stage 3. So stage 3 looks something like this. Gone a little bit over, but you'll get hopefully the gist of it. Okay. So this is our stage 3 in red, and you can see what's happening. You can see that what they're doing is they're going literally adding one piece the whole way around to cover each of the red squares. So we would do the same 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you can see this happening. So it's important that if you can't see it straight off, that you do something like this to identify what was the previous stage and how did we get to the next stage. So what kind of sequence, linear, quadratic, exponential, or none of these, do the areas follow? Justify your answer. So the first thing we need to be able to do is to figure out, well, what are the areas? So if we take from the picture on the previous slide, the first stage had 1 square unit. And remember they told us that each square had an area of 1 square unit. So in the second stage there was 5, the third stage there was 13, and the fourth stage was 25, and the fifth stage was 41. So what we're going to do, we're going to look at our first difference like we always do. So plus 4 plus 8 plus 12 plus 16. And it's definitely not linear, so then we look and say, well, is it quadratic? So I add 4, I add 4, and I add 4. So justify your answer. So the answer we have is, well, because it has a common second difference, so we'd say quadratic, and we would say common second difference. And we can show that easily here, common second difference. So that is justification enough to say that as a common second difference. So therefore it must be quadratic. Then it asks us to find the general formula of the area of stage n of the patterns where n is an element of the natural numbers. So we now know it's quadratic. So remember our formula for quadratics is Tn is equal to an squared plus bn plus c, where, and this was hugely important, 2a is equal to the second difference. So let's work that piece first. So 2a in this case is equal to 4, so a is equal to 2. So we can rewrite our Tn as 2n squared plus bn plus c. We then take two terms. I'm going to take T1 and T2 just because they're always the easiest to work with. And I'm going to say, well, if I sub in 1 instead of n, b times 1 plus c, I should get 1. So I get 2 plus b plus c equals 1. Take away a 2 from both sides, and I get b plus c equals minus 1. And that's my first equation. I then look at T2. Now you can take any terms you want, but T1 and T2 are always going to be the easiest because we have to square the number and do some multiplication. B times 2, plus B times 2, and that is equal to 5. So we get 2 times 2 is 4, times 2 is 8, plus 2b, apologies, I lost my plus c up here, plus c equals 5, plus 2b plus c equals 5. I subtract an 8 from both sides. 2b plus c is equal to minus 3, and that is equation 2. So now I have two equations in b and c, and I want to solve for them. So I'm going to use simultaneous equations, and I'm going to try and eliminate one of the letters. The easiest, if you stick to using T1 and T2, you're always going to be able to eliminate C quite easily. You can do that by simply multiplying the top line by minus 1 to change all of its signs. So you get minus b minus c equals 1, 2b plus c equals minus 3. You can see here the c's eliminate. You're left with b is equal to minus 2. We then go back to either equation. I'll take equation 1. B plus c equals minus 1. I actually know b is minus 2 plus c equals minus 1. I'm going to add a 2 to both sides. So I get minus 1 plus 2. So c is equal to 1. So that brings me back to writing my Tn. I'll do it back up here. Tn is equal to 2n squared minus 2n plus 1. And that is our general formula for the areas. Now, I know the first time you work through this, or if you haven't seen it in a while, it looks long and tedious, but it is quite quick and straightforward. And if you use the same terms each time, you're going to see that your simultaneous equations will always look alike, and you can work through this quite quickly. If you'd like to now validate that Tn, you can do that by subbing in a 1 and figure out do you get 1 as an answer, or you could sub in a 2 and you get 5 for an answer, or so on.